Today, we're diving into the fascinating and wide-ranging work of statistician Kenichi Satoh. We're going to explore how a core set of really powerful statistical models can act like a unifying lens, bringing incredibly different research fields into sharp focus.
All right, so let's start with a bit of a puzzle. What on earth could atomic bomb survivors, the way trees grow in Japan, and the evolution of CPR guidelines possibly have in common? I know, it sounds like a totally random collection of topics, right? But believe it or not, the answer is this powerful, flexible statistical toolkit that forms the common thread running through all of this amazing research.
So here's how we're going to break it all down. First, we'll look at the core statistical engine itself. Then, we'll see it in action everywhere from medicine to environmental science and even modern text analysis. We'll wrap things up by looking at where these tools are headed next and why collaboration is so key. Let's jump in.
Okay, first things first, we need to get a handle on the engine that's really driving all these discoveries. And I want to be clear, these aren't just dry formulas on a page. They are powerful frameworks for thinking about and for measuring the incredible complexity of the real world. A real cornerstone of this work is something called a Kenichi's Information Criterion, or AIC for short. The best way to think about it is as a guide for choosing the best model. See, when you're building a statistical model, you've always got this trade-off. If you add too few variables, your model is way too simple and misses the real story. But if you add too many, you start modeling random noise instead of the actual signal. AIC helps you find that sweet spot by putting a penalty on complexity, pushing us toward the most efficient model, the one that explains the data well with the fewest moving parts.
In this table, it just lays out that challenge perfectly. See those first few models? They're underspecified, too simple, and they miss the mark. The ones at the end? They're overspecified, way too complex, probably fitting to static. The job of the AIC is to be that smart guide, pointing us right to Model 5, the one that nails the balance between simplicity and accuracy to get closest to the truth.
So, at the end of the day, what we're really after is the Goldilocks model. You know the one. Not too simple, not too complex, but just right. And AIC is the tool that gives us a clear, principled way to find it.
Now, the second key tool in this engine is the varying coefficient growth curve model. And this thing is incredibly powerful. Instead of just assuming a relationship stays the same over time, like, say, the effect of a drug is identical at 1 month and 1 year, this model lets that relationship change and evolve. It lets us capture these dynamic, non-linear trends that are so much more true to what actually happens in the real world.
All right, so we've got our engine built. Now, let's fire it up and put it to work. Our first stop is the high-stakes world of health and medicine.
This is really where abstract theory meets a profound and sobering reality. The data you're looking at here comes from the atomic bomb survivor cohort. By applying these statistical models, researchers were able to quantify, over decades, the long-term cancer risk from radiation exposure. This work provided the critical evidence that continues to inform radiation protection standards all over the globe.
And here's another example of how these models can find the signal hidden in the noise. After the Fukushima nuclear accident, researchers used what's called Poisson regression to analyze thyroid screening data. The results were fascinating. They found a clear, statistically significant link between cancer cases and the local air dose rate. But, and this was the surprise, they found no significant link to the amount of iodine-131 in the soil. This helped untangle a super complicated exposure scenario on the ground.
And jumping to a more recent crisis, these same kinds of models were absolutely vital during the COVID-19 pandemic. A Cox regression analysis of patients in Tokyo identified the key things that put people at higher risk for hospitalization. Just look at that first bar. Patients age 60 and over had a hazard ratio of over 10. That means their risk was more than 10 times higher. That's the kind of clear, quantifiable result that directly told doctors which patients needed the closest watch.
Okay, now let's switch gears completely, because this is where you really start to see the incredible versatility of the statistical engine. We're about to apply the exact same foundational ideas to totally different fields.
So, how do you accurately model the growth of a tree? A standard model might not get the job done, but there's this really clever approach called the nuisance baseline model. It basically tells the model, hey, don't worry about the exact shape of the tree's natural growth curve. Just treat it as a nuisance and focus on how other things, like altitude, affect it. The result? A much more accurate fit and a way better understanding of what's actually driving the tree's growth. It's pretty smart.
And that same logic
It applies to social science, too. When researchers applied varying coefficient models to crime data in Columbus, Ohio, they asked a key question. Do things like housing costs affect crime the same way everywhere in the city? And the answer was a definite no. While the effective income was pretty steady, the model revealed that the impact of housing costs actually changed depending on the neighborhood. It's the kind of hidden spatial pattern a one-size-fits-all model would have totally missed.
And check this out. You can even apply these statistical methods to text. By using data mining on 15 years of CPR manuals, researchers could literally watch the core concepts evolve over time. Back in 2000, it was all about individual technique. By 2005, the big deal was the rate and cycle of compressions. 2010 was the year of that big switch to CAB. And by 2015, the whole conversation had shifted to the team. It just goes to show how you can quantitatively track major shifts in scientific thinking.
So it's clear this toolkit is powerful and incredibly versatile. But, data science never stands still. So let's look at how these methods are being adapted for the brand new challenges of modern, super high-dimensional data. Okay, so enter non-negative matrix factorization, or NMF, combined with vector autoregression. I know, it's a mouthful, but the idea behind it is actually really elegant. It's a method designed to take a huge, messy dataset, like infection data from tons of different places over time, and break it down into a few hidden, easy-to-understand patterns. And at the same time, it figures out how those patterns influence each other as time goes on.
And the results are just stunning. When this was applied to daily COVID-19 data from all across Japan, the model automatically found 4 distinct regions with their own unique infection patterns. Nobody told it where to look. It just found the hidden structure in the data, grouping areas into logical clusters, like urban centers, Western Japan, and coastal regions. It uncovered the secret dynamics of how the virus was really spreading.
So, you might be asking, just how well did this fancy model actually work? Well, the result was a coefficient of determination of 0.97. To put that in plain English, the model could explain 97% of the variation in the infection data. That's not just a good fit, that is an unbelievably precise and powerful model of a massively complex national system.
So, we've gone on quite a journey here, from core statistical theory all the way to real-world applications in medicine, ecology, sociology, and the frontiers of data science. And all of that brings us to what might be the most important point of all.
So what is the big story here? Well, first we've seen that a core set of foundational models can be a powerful, flexible engine for discovery. Second, we've watched that engine go to work solving real problems in everything from medicine to ecology. And third, we've seen that these tools are constantly evolving to take on the data challenges of tomorrow. And really, that's the story we've seen play out today. Statistics isn't just about crunching numbers. It's the bridge that connects abstract theory to tangible, real-world impact. It's the common language that allows an epidemiologist, an ecologist, and a data scientist to all get in the same room, understand each other, and create something new.
And that brings us to the final question, one that I'll leave with you. As researchers, we all have our own complex problems we're trying to solve. So what is that puzzle in your field? What's that one question that could be seen in a whole new light, or maybe even finally solved by looking at it through a new and powerful statistical lens? Thanks for tuning in.